All right, so in the last video we looked at a specific example of the extended fin problem, and now we're going to look at more general ODE. So nothing new in this video, just kind of a recap and pulling it all together in terms of the equations, the boundary conditions, and so on. And then we'll look at a specific example. So here's a general second order boundary value problem. The extended fin problem was a second order problem. But we're just going to generalize that. So we have a second order derivative d squared u dx squared, and that's a function of the independent variable x, the dependent variable u, and its first derivative du dx. And then this could be a nonlinear or a linear combination of the x, the u, du dx. Then we have boundary conditions. So we have Dirichlet boundary conditions where u is specified at the boundaries, say u at x is equal to a is capital A, and u at x equals b is capital B. Neumann is where instead of u being specified, the derivative of u is specified. So that's like a heat flux. This is like an isothermal boundary condition. So du dx is specified to be a or b at the two boundaries. And then finally a Robin boundary condition, which we introduced last time, is where you have a linear combination of the u and the du dx being specified at the boundary. So u at a, du dx at a, u at b, du dx at b. And then we have these p, q, and r coefficients which particularize it for the specific problem. So let's look at a second order linear boundary value problem. This is one that we can get the exact solution for, so I'll show you that down here. You can do Math 252 methods to get that. We'll have Dirichlet boundary conditions. U at x is equal to 0 is 1, and u at x is equal to 1 is 0. So here is that exact boundary condition which we'll use to compare our numerical solution. So the f, the g, and the h now are 2, 1, and 0. Those were introduced in the last video. So f is 2, g is 1, h is 0. The tridiagonal system of equations that we get is here. That's the finite difference equation, again with the a, the b, and the c. Now you'll notice there's no subscripts on the a, b, c, and d. That's because they're now constants. So a is 1 minus a half delta x f, but f is 2. So then a is 1 minus delta x. Again, it's just a constant. C is the same thing, but it's a plus sign instead of a minus sign. B is minus 2 plus delta x squared times g, but g is just equal to 1. So b is minus 2 plus delta x squared. And then finally, d is delta x squared times h, but h is 0, so d is 0 in this case. The two boundary conditions, u sub 1, remember that's shorthand for u at x equals a, which is the left boundary. So u1 is a, and in this case that's 1. And then at the right boundary, u at capital I plus 1 is b, and in this case that is 0. So as we did in the extended fin case, all the stuff that we know goes on the right. So because we know u1 and ui plus 1, those get moved over to the right-hand side, and therefore they go in the d. So here for d2, we end up with d minus a. For d capital I, we end up with d is equal to just d. So here's an example of a numerical solution for that problem. The numerical solution are the dots. There's 21 of them, 20 intervals. So there's 21 points, including the boundaries. And remember, u at x is equal to 0 is 1, and u at x is equal to 1 is 0. So those are the boundary conditions. Those are fixed. The solid line is the exact solution, and the dots are the numerical solution. And you can see the agreement is very good. In tabular form, I'm just showing every other point. So 1, 3, 5, 7, 9, up to 21. And the value of x corresponding, so the left boundary and the right boundary. And then the numerical solution at each of those alternate points, every other point. And then the corresponding exact solution. You can see they're very close. Here's the absolute error, which is just the difference between them. You'll notice there is no error at the left or right boundary, and that's because the boundary conditions are known exactly, so there's no numerical error at the boundaries. the maximum error is actually near the middle, not exactly in the middle, but near the middle. So that's the maximum error. And you can see it is quite small with 21 points. So that's typical for a problem with Dirichlet boundary conditions. The error is 0 at the boundaries and maximum somewhere in the interior. If you look at the effect of the resolution, so we're going to look at the effect of increasing I. I just showed you where I is 20, but let's try 5, 10, 20, and 40, so doubling the number of intervals each time, and get the maximum error and see how the maximum error changes as we increase the resolution. So for comparison, here is delta x squared. Remember, the error is order delta x squared. It's not equal to delta x squared, but it's of the same order. So that means that we can multiply some coefficient times delta x squared to get the actual error. We don't know what that coefficient is. We don't actually care. But as you can see, obviously, as we increase the number of intervals, the delta x squared goes down very quickly, and that's because it's squared. Likewise, the maximum error, so for 5 points we get 0.002639, and then 10, 20, and 40. So obviously, as you'd expect, the error goes down each time. But what you'll notice even more, if you look at it more carefully, is the amount that the error goes down is exactly what you'd expect. And I'll explain why that is in a second. So the error is going down by a factor of 4 each time. You say, okay, well, I'm doubling the number of points, so that means I'm halving delta x. Delta x for 10 is half that for 5, for 20 is half that for 10, for 40 is half that for 20. So every time I do this, I'm halving delta x, and then the error is going down by a factor of 4. And it's actually very precise. Precisely a factor of 4. So the reason for that is, remember that the second order accuracy means that we have order delta x squared. So if I have delta x, then the error goes down by 1/2 squared. 1/2 squared, of course, is 1/4. So it goes down by a factor of 4 each time, and that's exactly what you expect. So if it's order delta x, it'll go down by a factor of 2 each time. You double the grid. If it's order delta x squared, it goes down by a factor of 4. So that's why the error goes down so quickly. Let me discuss a little bit some debugging suggestions. We haven't talked a lot about debugging. You've probably been learning through the problem sets that the debugging is the worst part, the most frustrating part of programming. Programming is actually kind of fun to tell the computer what to do and see it do it for you. And once you've got the program working, you can reuse it, and it's very, very enjoyable to see that. But the debugging part is the most complicated, most frustrating, as I said. My first comment is what not to do. Do not use the shotgun approach to debugging. So the shotgun is you fire it out and things go off in all different directions. So the shotgun approach to debugging is you program it, you hit the run button, you don't get the right answer. So you just go in and you start changing stuff. Let me try this, let me try that, let me change this, let me change that. It rarely ever works. Your hope is that in a very short period of time, you can get the thing to work and you'll be done. It's usually much more efficient, time efficient, and reduces your stress and frustration significantly to use a more methodical debugging approach. And know that it's going to take some time. It's not unusual for, if 1 unit of time is how long you spend writing the code, it's not unusual for complicated codes to spend at least 10 times as much time as writing it to debug it. So just know that that's going to be the case. And so be methodical, take a more measured approach. So for example, one thing that maybe is counterintuitive, you're looking for where the errors are, but it's just as useful and valuable to find where the errors aren't. And the reason why I mention that is it's an argument for modular programming, which we've discussed before. So modular programming, you break up your overall code into little pieces, and each little piece, each little module, typically that's a separate function or a separate procedure, is standalone. So for example, the Thomas algorithm is a standalone function. Once you've tested it, once you have it working, you know it works, and then you can reuse it. Anytime you're trying to solve a tridiagonal system of equations, you call your Thomas algorithm, you give it the A, B, C, and D, gives you the solution, and you're done. So if you have a big long code, and one part of that code is to do the Thomas call, you know the Thomas algorithm is working, you know it's been debugged previously, you know it gives the right answer for various different types of boundary conditions and so forth. So you can reuse it, and you know that the problem, the bug, is not in the Thomas algorithm in that example. So you look elsewhere. It narrows down where to look. So you're carving out the code. I know this is working, I know this is working, I know this is working, so the error has to be somewhere in here. And this is just, the last comment is really more for me, but I actually really appreciate one aspect of coding, and that is essentially, if you think about it, there's no partial credit. Now I give partial credit even if the code's not working right, but the coding itself, it gives no partial credit. So again, this is a frustrating aspect of coding. So you can be debugging, and you feel like you're not getting anywhere. In fact, you are improving the code, but until it works, until it actually does give the correct answer, you don't feel like it's done. And I find pedagogically, which is a fancy word for teaching, I find pedagogically that there's a lot of value in that. There's no partial credit for coding. It has to work properly, it has to be completely correct, otherwise it won't give you the right solution. Okay, so that's it for ODEs. Next we're going to start looking at partial differential equations. There's whole books on this, and we're just going to look at a couple of things that we've done before and how they can be extended to solving PDEs. So we'll talk about that in the next video.